Okay, so we're going to take a look at section 3.2 about the mean value theorem. And hopefully before watching this video, you took a look at that Desmos activity that we hopefully did in class this morning, if you're watching this on Wednesday, to kind of show what this is really all about. And the whole point of the mean value theorem is under certain circumstances, in certain situations, if we draw in the slope of our secant line. So let me take a look at some function over here from A to B. I've got some function over there. If I draw in the secant line, somewhere my tangent line will have the same slope. So let's see, I want a slope of this. Over here I've got a slope of that, and that, and that, and that, and that, and that, and that. Oh, this kind of looks right. Over here, the slope of my tangent line is going to be equal to the slope of my secant line. We saw in that activity we could always make this work as long as our original function was continuous and differentiable. Let me kind of put this in writing. So theorem. And specifically, this is called the mean value theorem. And it says, if our function f of x is, first of all, we have to be continuous. And I don't even care about continuous everywhere, just continuous on some closed interval from A to B. And I also have to be differentiable, no sharp turns, no vertical tangents. Differentiable on, actually doesn't even have to be a closed interval, could be differentiable on an open interval. I could have an issue at A or B and the mean value theorem will still apply. Then, there exists a C value, a particular x, in my interval from A to B, such that the slope of the secant line equals the slope of that tangent line. What's the slope of this secant line? Well, I think I can just do f of b minus f of a over b minus a. That is the slope of the secant line. And that slope is also sometimes called the mean value. This tangent line at x equals c, what's the slope of a tangent line? A derivative, f prime of c. That's the slope of some tangent line. If I have a continuous function on a closed interval and differentiable on a related open interval, then I'm guaranteed that somewhere the slope of my secant line must equal the slope of some tangent line. I can find the slope of my secant line. Somewhere my tangent line will have the same slope. Let me show you how we can use this. And throughout all these examples, we'll go through some calculations, but we'll also take a look at some graphs through Desmos. Before we go on, though, I'm going to make the video pause if you need a moment to copy this down. Then, let's take a look at this problem. We want to determine if the mean value theorem can be applied if so, we're going to find the slope that is guaranteed, the slope of our secant line, and then find the value of c such that f prime of c equals f of b minus f of a over b minus a. We're not going to worry so much about that right now. I'm going to make the video pause. Please copy this down. Oh, I never actually gave you a function. We're going to take a look at the function f of x equals 3x squared plus 6x minus 5. And I'm going to deal with this on the closed interval from -2 to 1. First of all, is my function f of x continuous on the closed interval from -2 to 1? Well, sure. It's a polynomial. All polynomial functions are continuous. I do need to actually state this, though. So I'm going to say, number one, f of x is continuous on my closed interval from -2 to 1. Because it's a polynomial, no denominators, no issues, whatever. To show that it's differentiable, well, let's find the derivative and make sure our derivative doesn't have any issues. Our derivative needs to be continuous as well. F prime of x equals 6x plus 6. I think that thing is continuous. Therefore, I can say that my original function f of x is differentiable on the open interval -2 to 1. No denominators, no issues. Therefore, the mean value theorem applies. The mean value theorem applies. Which means that the slope of the secant line will have to equal the slope of some tangent line. Let's figure out that slope that's guaranteed. The slope of my secant line is going to equal f of 1 minus f of -2 over 1 minus -2. F of 1, well, that's 3 times 1 squared plus 6 times 1 minus 5 minus f of 2 is 3 times, another layer of parentheses here, -2 squared plus 6 times -2 minus 5 all over 1 minus -2. You're going to take a moment, you're going to simplify that, and you're going to tell me what slope is guaranteed. Three plus 6 minus 5 minus, I'll keep the parentheses in for right now. -2 squared is 4, 3 times 4 is 12, minus 12, minus 5 over 3. 3 plus 6 minus 5 minus, those cancel, minus -5 gives us a plus 5 over 3. I'm thinking 9 over 3. I'm thinking 3. Somewhere, our slope has got to be 3. Well, now that I know that somewhere my slope has to be 3, I want to figure out where exactly that's going to happen. To find where this occurs, well, I'm just going to set my slope, my derivative, equal to 3, and I'm going to solve. I'm going to say f prime of x equals 3, 6x plus 6 equals 3, 6x equals -3, x equals -1/2. When x equals -1/2, the slope of the tangent line will equal the slope of the secant line. I think we need to check this. The video is going to pause for a moment and direct you to a Desmos little activity. Go there and see if when x equals -1/2, the slope of the tangent line equals the slope of the secant line. Well, hopefully you saw that that worked. Let's take a look at another example or two. I am not going to bother writing out all those directions again. Same directions as before. We want to determine if the mean value theorem can be applied. And then if so, we'll find the slope guaranteed. And the value of c is such that, well, f prime of c equals that slope we're looking for. I want to look at the function f of x equals the square root of x minus 1. And I want to deal with this on the closed interval from 2 to 5. Before I go and use my mean value theorem, I have to explicitly check the requirements. If you just start doing these problems without that, you will not get full credit for these, neither on the homework nor when it shows up on a test, nor certainly the AP exam. Is this function continuous everywhere on 2 to 5? Sure it is. F of x is continuous on that closed interval from 2 to 5. Take a moment, get your derivative, and tell me if we're differentiable on the open interval from 2 to 5. Okay, so f prime of x is going to equal 1/2 times x minus 1 to the negative 1/2, or 1 over 2 root x minus 1. I have some issues here at x equals 1. But I don't care about that. I care about between 2 and 5, and there are no issues there. Therefore, since that's my derivative, I can say the original function f of x is differentiable on the open interval from 2 to 5. Please make sure you're saying f of x is differentiable, not f prime of x is differentiable. That means something different. My original function's derivative is continuous is what I'm saying when I state f of x is differentiable on 2 to 5. So, yes, the mean value theorem can be applied. Okay, I want you to take a moment and tell me the slope that is guaranteed. Do your f of b minus f of a over b minus a. Okay, f of 5 is 5 minus 1, f of 2 is, sorry, not 5 minus 1, square root of 5 minus 1, f of 2 is square root of 2 minus 1, over 5 minus 2 over 3, square root of 4, minus square root of 1 over 3, 2 minus 1 over 3. Your slope guaranteed is 1/3. I now want to figure out where my function has a slope of 1/3. I want to set f prime of x equal to 1/3. Okay, well, f prime of x I know is 1 over 2 root x minus 1. I'm going to say that that equals 1/3. You take a moment and tell me where this happens. Okay, I'm going to cross multiply. I'm going to get 3 equals 2 root x minus 1. I'm going to divide by 2. 3 halves equals square root of x minus 1. I'm going to square both sides. X minus 1 equals 3 halves squared. X minus 1 equals 9/4. Add 1. X is going to equal 9/4 plus 1, or 9/4 plus 4/4. X is going to equal 13/4. When x equals 13/4, oh, you can't see any of that work. Sorry about that. When x equals 13/4, your slope of your function will equal 1/3, which is the same as the slope of the secant line. Again, go and take a look at Desmos and see if this actually works. So we're going to take a look at 2 more mean value theorem examples. I'm not going to write the directions, same directions they've always been. We're going to verify that the mean value theorem applies, and then if it does, we are going to find the slope of the secant line and find where the derivative has that value of the slope. So we're going to take a look at the function f of x equals 3x to the 2/3. We're going to deal with this on -1 to 1. First question for you. Is that function continuous on the interval from -1 to 1? Sure it is. I have no denominators. I have no pieces of piecewise functions or whatever. I can just state f of x is continuous on negative 1 to 1. Find the derivative and make sure it's differentiable. Is this differentiable on negative 1 to 1? Okay, so f prime of x is going to equal 3 times 2/3 x to the negative 1/3. This is 2 over x to the 1/3. I have a problem at x equals 0, which is in my interval. That means this function f of x, my original function f of x, is not differentiable at x equals 0. And because of this, the mean value theorem doesn't apply. I can't guarantee that there's a place where the slope of the secant line through negative 1 comma 1 equals the slope of the tangent line. Let's check this in Desmos. See what happens. Okay, hopefully you see that, yeah, there is no place where the slope of the tangent line equals the slope of that secant line. This is an example of why we need that differentiable condition. Just being continuous isn't good enough. Let's take a look at the function f of x equals 1 over x on the same interval, negative 1 to 1. Go through your two checks. Number 1, is that function continuous on the interval from negative 1 to 1? I don't think so. I think there's a problem at x equals 0. F of x is not continuous at x equals 0. Not even going to bother going on to the differential part, because if we're not continuous, that's good enough for the mean value theorem to not apply. The mean value theorem doesn't apply. Which means that we can find the slope of the secant line, but we are not guaranteed that somewhere the derivative will have that same value. Let's test this in Desmos. Once again, go to the link that's going to show up. You'll see the slope of the secant line. Try to show that there's no place where the tangent line will have that slope. And I think that's about all that I want to say for this video.